गुरुभ्यो नमः। हरिः ओम्। ॐ सहना भवतु सहनो भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु।
एक्सपेरिमेंट किया ना।
शांति शांति शांति। Presence of the divine. Welcome to the final session of the third international conference on Eastern Medicine. The physics being led by report. So for this session we have a talk by Dr. Pankaj Kumar Giri, followed by the presentations of various research scholars. Dr. Pankaj Kumar Giri, just now I was trying to talk to him, has done his MSc from Professional University, and then did his PhD from IUSC, but basically, of course, I was in Central Institute Jharkhand, and currently he is a research associate of the ATCDY Consortium for Scientific Research, and is based at Kolkata. And I request Dr. Pankaj Giri to share his research with us. Dr. Pankaj, over to you.
Thank you so much, sir, for the nice introduction. Let's share my slide and is it visible, sir?
Yes.
Okay, very good afternoon to one and all. I'd like to thank the organizer for giving me this opportunity to present our research plan, what we are actually planning to do at our center, UGC-ACSR Kolkata. So, I'll be mainly talking about today the topic of alpha-induced radioisotope products for medical use, and for doing so, the methods and modeling, what we can imply to do the production through the alpha-induced field. So this will be my talk overview. So first of all, I'll be talking a little bit about the radioisotopes of medical use, importance of alpha-induced reaction, then codes for processor calculation, nuclear modeling, measure and interpretation, particularly what I designed for this talk, and then I quickly summarize my talk and then outlook for this particular topic. So let me first actually give a bit of picture about the radioisotopes of medical. The radioisotopes are, as I actually listening about the one of the talk last day, that they are talking about the irradiation of the tissues, the gamma attenuation technique. So basically I'll be elaborate little more into this field, the application field of this nuclear physics aspect, in order to explain the radioisotope production. So these are the techniques will be used in the medical field with the medical imaging technique, where we can use the radioisotope. Radiation therapy are there, and radionuclide therapy is also there. Then radiopharmaceutical, which is one of the important aspects, and then we can have the sterilization of medical equipment. I'll explain one by one what are the techniques. So as I illustrated this one here, the PET imaging, which is the position emitting tomography, basically used for the imaging of the different metastatic kind of deformation in our body, or we can have the pictorial representation where the particular deformation are occurred in our body. But so I'll be explaining about the PET scanning in the next slide. So let's start with this radiation therapy. Radiation therapy, as I explained, that this is one of the techniques which required we are giving the radiation to the particular part of the body which are deformed due to the cancer or information about the position. And we can irradiate a particular amount of radiation dose in order to kill that particular organ and you can eventually cure the patient. But in the radionuclide therapy, what we are actually do that we give the particular radioisotope in some sort of combining agent like compound, protein compound, and it will be injected inside the body, and that compound will accumulate to the tumor area or the tumor metastatic region, and that radioisotope will continuously emit the radiation and eventually will cure the tumor cell. And the sterilization part to use before the operation or any kind of the medical use, there are different kind of equipment that can be also sterilized, or we can sterilize using the radiation. So these are some of the applications for the radioisotope in the medical application. So let me come to the brief of the what is actual the positron emission tomography. In positron emission tomography, we can understand by seeing this pictorial representation that we have a particular radioisotope, or we say the radio labeling, then we'll combine with some sort of chemical molecule and form a PET tracer which will emit the positron, and then we inject that particular compound or PET tracer inside the patient body, which combine with the which will eventually emit the photon energy, and then that will detect through the gamma detectors and will build a 3D model of our body with mixing with that coincidence with that particular gamma emission, and we will have the image. And there I bit more elaborated on this topic, that the positron emission tomography. So the beta particle, the positron will be emitted from our compound. It will collide with the electron which will be emitted from the tissue. Then it will emit a 2 gamma rays which will be 511 keV annihilation gamma photopic, and that will be detected throughout the array of our gamma detector or PET detector rings. So in that way we are having this kind of picture. So if we have only the computer tomography, then we can have only this type of the detailed organ image. But when we are actually injecting one of the tracer inside our body, then it will only highlight the particular high metabolism part of our body. Then when we are combining these two CT image and the PET scan, then we have the detailed picture, PET image, which we are calling. Then by seeing this PET image, the doctor
अच्छा अब शायद पूरी सारा प्रोग्राम
अभी इनकी टॉक है लास्ट ईयर, इसके बाद फिर से ओरल प्रेजेंटेशन है 5, पिछले 2-3 रहे, 8 एक हो गई, 8-9 ओरल प्रेजेंटेशन, फिर लास्ट में एक ही जैन सर का लेक्चर।
लड़की चीज़ें भी रही है ना तीसरी साहू
ये तीसरी साहू एक है, अभी तक उसी में इश्तियाक है, सुशील है, ये तीसरी हो गई, इश्तियाक हो गए, सुशील 3 हो गई है, और 5 नीचे 8, एक फर्स्ट और पिछले कल का भी बचा, और कोई वो चिराग चिरूग लाश सिंह वो आता है तो
चलो इनका तो छोटा सी होगा एक ही दिन है ना ये तो प्रत्युत्तर बाबन साहब ने दिया, विश्वनाथ स्वयं ने देना है
नहीं वृत्तबाबू साहू का हो गया, विश्वनाथ स्वयं का ये था, स्वयं जो था
जो भी आया था स्वयं का।
हाँ वो विश्वनाथ स्वयं था। और इसके बाद ये तीसरी के
क्या
बाद
अहमद का
इश्तियाक के बाद है सुशील।
सही तो दो तो लाख के सब स्टूडेंट नवजोत कौर, दानी रोज, नबील सलीम, ज्योतिष के गोकुल जगह तरीके के स्टूडेंट। मुझे लगता है NIT जहाँ पर है ना ये लोग, वहाँ पर भी नेशनल एजुकेशन पॉलिसी लागू हुई होगी लगता है, तभी ये इनसे इंटर क्राइटेरिया कंप्लीट करवा रहे हैं, नहीं तो मास्टर्स
चले जाता है उसमें।
क्या जाता है जो भी ऑफ है
नहीं, OBS यूज़ करा ना इंटरनली सिस्टम से, उसमें नहीं है। अगर वो बंद कर देंगे तो जो इसमें आ रहा है वो कुछ नहीं, वहाँ कोई नहीं होता है, वहाँ कोई नहीं होता। इंग्लिश का आ गया आज, इंग्लिश की लिस्ट निकाली है कमीशन में आज। हमारी आएगी सोमवार को।
अगर ललित आएंगे सोमवार को, तुमने बोला था सोमवार को, और मेरी आवाज़ आएगी देखना थोड़ी देर बाद। बहुत कम आवाज़ आती है सही है यार, इसमें रहता है बहुत कम हो गया। One watching. आज भी तो हुआ नहीं क्या, वो जो उनका वो देना था प्रेजेंटर का जो बताना था, वो भी नहीं आज हुआ, चलने के रही सर को भेजा हूँ।
accelerator institute like IUS, CTIF or BRC and VCC like in India or abroad, there are many more. So these are the very expensive affair. So in order to go through a full-fledged experiment, one need to be sure by doing like the theoretical estimation or modeling that okay, so I'll be finding or at least expect my result at that particular energy range, or I'll take this much of thickness of the target. So these aspects are the important ones. So we'll be addressing today that aspect. So there are some model code which are available in the market, like I would say, but the codes have its own limitation. These three what I listed over here are the more comprehensive one. Why more comprehensive one? Because the Talis, Ampere and the Alice code will include, or I would not say these are the directly code, but these are the platform where will imply our particular model, or these platforms giving us the choice to choose our particular model which we want to club with or add, or then eventually do our calculation to find out the result. So these models or these platforms are incorporated the models for the direct nuclear reaction, pre-equilibrium nuclear reaction and compound nuclear reaction. So I'll be basically focused today on the Talis. Okay, so before going to the nuclear modeling, let me little bit speak about the different stages of the nuclear reaction. When our projectile collide with the target, that projectile will eventually target and form a compound nucleus. That compound nucleus will be may go through the fission, or eventually the fission will emit the multi-compound emission, and or if it is forming the compound or composite system, then we will expect our cross section or the energy range at that this particular spectrum will be observed. But what if that system will not go to the directly to the compound nucleus fusion, and it will get more time interact with the target, then it will prolong the process, and then we'll have observe the compound as well as the pre-equilibrium process also. So the spectrum will elongated through the energy like this, and then eventually if we have the more energy in the projectile, then we will get also discrete level, that is the direct nuclear reaction. So mainly we can categorize our nuclear reaction like three category, that is will be C part, C, B and D, that will be compound, pre-equilibrium and direct. Why we need the idea of this type of nuclear reaction? Let me explain with this particular example of alpha induced reaction of with copper or 66 gallium. So these are the experimental data, and I placed here the only one code that is based for which is based on the compound nuclear reaction mechanism only. So this code will not take into the consideration for the pre-equilibrium or direct reaction. So it will only predict the compound nuclear process. So for the particular residue formation, we can see this baseline is explaining well or the matching well with the experimental cross section. But when the energy is increasing, this code is deviating from this experimental data. So this is the only reason why it will be happening, that this code has the limitation, it would only consider the compound part. But what if one code is considering the compound part and the pre-equilibrium, then maybe we can have the better result. So we try to figure it out that why this is. So from the Talis we include the compound part as well as the pre-equilibrium part also, and choosing a appropriate level density model for this particular region. then we can observe that this experimental data is nicely fitted with the theoretical prediction. Yes, of course, there are some mismatch are there because we can fine tune the model further, but it will explain our experimental data much more accuracy than that of the one code which will only considering the compound part. So that's why the theoretical modeling or the having the theoretical modeling as well as having the proper knowledge of the process which need to be incorporated before running a particular code is very important. So let me just point out what are the different kind of models are included in the TALIS. For the optical model potential, there are several models like some are the local and some are the global potential models are also there. And for semi microscopic nuclear spherical optical models from this particular model is also provided in the TALIS code. And for the level density, we have the phenomenological and microscopical level density model. For the phenomenological level density model, we have the constant temperature Fermi gas model, backshifted Fermi gas model, generalized superfluid model. For the microscopic model, we have the Scheimer Hartree-Fock-Bogleberg model, and these are others which can be used for the microscopic analysis. And also the adjustable parameter, that the level density parameter constant, level density parameter A spin cutoff model, these are also included in this platform. User can select their particular model for the level density for a specific nuclear reaction. And for the photon strength function, there are similarly have the phenomenological and microscopic models are there. And for pre-equilibrium models, there are several models are included in the TALIS code, like the 2-component and 1-component excitation model. And for the total pre-equilibrium cross-section model, we have this kind of models are included in this platform. So there are variety of choice which will be used to explain the physics behind the particular nuclear reaction or optimize the prediction prediction over the experimental data. So I designed for this particular talk in order to apply some of the modeling to produce the radioisotope. We indexed from the IAEA website and go for the positron emitter radioisotopes. These are the standard indexed IAEA radioisotope for the medical application. So I just collect or took the information about the alpha induced nuclear reaction for the present study, and we do the modeling. So this is the structure we first imply on our primary model of the radioisotope production. So we basically took the optical model and the nuclear structure part. So as you can see, when we are fixing the level density parameter and varies the optical model, the alpha optical model parameter, these are sensitive towards the lower energy side, throughout from the lower low jet target to high jet target like bismuth. So the optical model will be sensitive towards the low energy side. If someone is planning to do the production of the radioisotope in the lower energy side, so he might be very careful about the choosing the proper optical model, alpha optical model. But when we are fixing the alpha optical model and vary the level density model, these are sensitive towards the higher energy side. So this label density parameter or the choosing of label density model will be sensitive towards the higher energy side. So one need to choose accordingly to their need. And then when we are applying these models with the IEA index data set, you can observe that this the compound nucleus model, the PACE 4, is completely offset with the experimental data, and the maroon line is basically the best fit of the experimental data suggested by IAEA, and these blue lines is our model prediction with tallies. We can see that our model prediction is giving the much better result than that of the other models which are only considering the compound nuclear process. So one need to choose carefully the label density model, optical model parameter, and these parameters are fixed during the calculation, found best fit during the calculation. The alpha optical model of this particular model, and for gamma strength function Brink axial Lorentz model, and the pre-equilibrium model for exciton model is been used for the particular model prediction. And we also estimate the thick target yield for that particular radioisotope, and we can find that our model prediction is agreeing well with the experimental prediction. Yes, there is still scope for improvement in the theoretical modeling, and similarly we also put an effort for the higher Z target isotopes, radioisotopes, and we can find that with the choosing appropriate model, we can really fit our data, experimental data, with the model prediction. And why we are doing actually this kind of exercise? Because as we can see that so far for this particular, if I am taking this particular example of 118 Telrum, that the experimental data are not available in this particular energy range, but for suggesting one radioisotope which will be an alternative for the conventional radioisotope for a medical application, we need to produce that particular radioisotope in a bulk manner. So we need to find a energy range where this particular radioisotope will be produced optimally or in a optimum quantity. Like the experimentally data are available only into this region, but if I am to produce this particular radioisotope, I may took the energy range from the 40 to 60 MeV, where I could produce this particular radioisotope in a bulk or more quantity. And lastly, I will be showing this particular radioisotope which will be of great importance in the target radiation therapy. That will be bismuth 209 bismuth using the alpha, and we can produce this 211 astatine, and our model prediction show that the production is agreeing well with the experimental data, and we can see that the optimal production range will be above 40 to 50 MeV. And this particular radioisotope is a club with a molecule, protein molecule, and can lock into the cancer cell that will be continuously emitting alpha particle, which will eventually cure this tumorous cell or the cancer cell. And let me just quickly summarize my talk, that the radioisotope produced by the alpha particle irradiation can be used for the variety of medical application like medical imaging, targeted alpha therapy, and radiotherapy. Modeling and simulation technique can be used to optimize the production of alpha in this radioisotope, and taking into account the factors such as target design, beam energy, and irradiation time. The production of alpha emitting radioisotope using alpha particle radiation is an attractive option for medical application. Alpha induced radioisotope production is a rapidly developing field with ongoing research and focus on the improving the production methods. Overall, the use of the alpha-induced radioisotope production for medical application has the potential to revolutionize the cancer treatment and improve the patient outcomes. However, continued research and development are necessary. And these are the some experiments recently performed at the BCC. So by looking into and taking these parameter constant which are used for this experiment, we will be planning our experimental procedure from our center. And I'm happy to actually highlight this one from the BCC website that 201 thallium radioisotope have been successfully produced on the 25th January 2021 for the first time in India for the BCC medical cyclotron from the thallium 203 target. And the outcome of our work is optimization of input parameter for model prediction that will actually done in the first stage. Now we are in the second stage of our plan, the experiment for the possible radioisotope. Then we will move to the third and fourth stage, that will be the method to develop the extract this particular radioisotope, then radiobiological implementation. And these are some radioisotope which we are actually focusing to produce in the optimum quantity, and this highlighted region will be probed through the BCC cyclotron through the alpha beam. And quickly just a overview of our UGC CSR. There are actually 4 centers. One is at the one is Indore Center, another one is Kolkata, from where I'm actually belong, and Mumbai Center. One is the Kalpakam Node. The UGC DCSR Kolkata is basically concentrating on the use of ion beam and radiation in the basic and applied science. It's already contributed effectively. We know all about the INGA facility, National Gamma Ray facility, and support at the Center for the Material Modification using the ion implantation. It's carry out the trace element study using the PIXI with the 3 MeV tandem accelerator IOP Bhubaneswar, and by using the in-house EDXRF and micro XRF facility are also there. Our center have in-house research of this particular category: nuclear spectroscopy, material science, radiation chemistry, radiation stress biology, and research are also carried out with collaboration with the VCC, ion implantation setup from the keV to MeV range, positron annihilation setup, atomic force microscope, and medical cyclotron facility. And if someone wish to avail this kind of facility from the UGC DACSR, there is basically a 7-step process. First of all, you can visit to the csr.rs.in website and register yourself to the CSR user portal. Then you can apply for, there are 2 categories. One is one-time research proposal and the long-term research proposal with funding for the 3 years. Then you can apply for the particular facility which we want to apply for. Then you can have this facility free of cost, of course. And these are the team for the radioisotope production. And first of all, I'd like to thank my director, Dr. Sandeep Bugre, which is the constant motivation for our work, and my PDF mentor, Dr. Rajshri Rao, and BCC, from the BCC I have Gopal Mukherjee and Sandipan Das Gupta. And of course, we are open for the collaboration for this particular kind of research work. And these are our vibrant group of research scholars working in the various field of our research group. And this work is funded by the Government of India, SCRB DST.
Thank you, Dr. Pankaj. Thanks a lot. Yeah. From the Chairman, sir, any comments?
it's quite interesting to see various aspects that are going on in India, and especially I wish I had known it a bit earlier than this, because we are also focusing upon isotopes and various uses of isotopes, and one of them, of course, is medical uses. And I had known a bit before, like we're having a conference
Yes.
in July.
July.
11th ICA.org. And like you mentioned, the target alpha therapy is becoming increasingly important. And
Yes,
I think you guys are going in the right direction. I wish you all the best.
Thank you.
And experimentation is a hard stuff, like you mentioned. Of course, modeling is modeling, but then one has to validate them by experimentations. And I think you're all set very well. Congratulations and good job. Thank you.
Thank you. Thank you so much, sir.
Thank you, sir. Any questions? Okay. So thank you very much, Dr. Pankaj. We look forward. I hope that somebody, at least some people, will try to collaborate with you. Okay. And now we move to a final session of oral presentations. Are you ready now, Itishri?
Yes, sir, I'm ready.
Yeah, you can start.
Yes, sir.
Itishri is an MSc student, I think, from Lasers group. Yeah.
Yes, sir.
Yeah. Present your screen now.
Yes, sir. Sir, is it visible?
Not visible.
Yes, sir. So wait a minute, I'm trying. I don't know.
Okay, you take help from someone. In the meanwhile, we'll start with Ishtiaq Ahmed. I think Ishtiaq Ahmed is ready.
Yes, sir, I am here.
Yeah, please, you can start with your presentation. Ishtiaq Ahmed is one of the research scholars currently at IUSA, New Delhi. Yeah.
I think this is already sharing the screen, so.
Okay, let us continue then.
Okay.
Good job, Ishtiaq. Go for it.
Yes, sir.
You have to show your presentation screen now.
Yes, sir.
Shift to your presentation screen. Yes, good. Now go to full screen mode if possible.
Yes.
Good, very good. Now start.
Yes. So I'm Itishri Sahu, and I'm doing LLB second year under supervisor of Professor Ujjwal Lahasar, and my topic is nucleus elastic thread scattering with manifold plus Wolfram potential. So the contents are given below. So we are taking our two charge particles here. The interaction between two charge particles, and we will briefly discuss about an introduction and the methodology we use here, and then the elastic scattering between the proton and oxygen system, and in the end we will discuss about the results and discussion. And we know that the nuclear scattering involving charged particles, and the scattering takes place under the action of two potentials. So here the two potential we are taking, that one is the nuclear potential and the other one is the electromagnetic potential. So we know that the electromagnetic interaction is of infinitely long range. So in reality, the electromagnetic interaction becomes scaled at certain distances. So we are taking electromagnetic interaction at short distances potentials to treat the charged particles scattering with the formalism of ordinary scattering theory. So here we are taking the electromagnetic as the Holstein potential and the nuclear part as the Manning-Rosen potential. So the different types of local potential we are using as one was the Holstein potential and Manning-Rosen potential. And here we are taking screen radius as A and B as for the Holstein potential and the Manning-Rosen potential respectively. So for the two charged particles we are taking for the proton and oxygen, for the atomic plus nuclear potential at the center of mass of energy, the Schrodinger equation we can write as given as equation 1, the double derivative plus the k square minus v effective r and phi L k r equal to 0, where k is the center of mass of energy and v effective as the addition of the Holstein and the Rosen-Manning potential. And we are using the following transformation as equation given by equation 2 phi L k r, and we are using del as the for all particle where given that is the dimensionless quantity and L takes from 0, 1, 2, 3 and so on. So here we are calculating for S wave only, and using equation 2 in equation 1 and doing some simplification, we will arrive at equation 4. And in equation 4 we can see that equation 4 on the RHS side as z is less than 1, so we retain only one first order term in z at right hand side, and then simplifying the term, the corresponding integral equation with the regular boundary, we will found that as given as equation 5, where the z is where the w is the Wronskian, we are using as equation 6, and gkz is the Gaussian hypergeometric function. Sorry, f is the Gaussian hypergeometric function and gkz is the power series we are using. And to solve the equation, to expand, we have to expand the gkz in power series as given as equation 7, and using equation 6 and 7 and putting in equation 5, we will arrive at equation 8, which is the integral representation of just function in terms of interaction potential V effective R given as the just function Fk is equal to 1 plus integration of 0 to infinity V effective R into e to the power ikr and phi kr dr. In the results, we will find that in our approach that Josh function is the most important quantity, because from Josh function we can calculate the bound state and the scattering phase shift as well. So that's why Josh function is the most important quantity here, and the roots of the Josh function that lies in the upper half k-Planck plane that is corresponding to the bound state energy of the related system. So when we will put k equal to I kappa, that then the Josh function will be 0. Then we will find that our binding energy of the system. So here we are using for Holstein potential V0A equal to 2k gamma, where we are taking the screen radius A equal to 55 femtometer for the Holstein potential, and the quantity we take 2k gamma is equal to 0.5255 femtometer inverse, and the paramethrogen potential we take alpha is equal to 0.05 and B 1.195 centimeter and A 0.458 for proton oxygen system. And using all this data and running in a programming language, and you will find that these parameter is fitted well with the correct binding energy for a fluorine 17 nucleus. So the relationship between the phase shift and the just function is that the phase shift is equal to the tan inverse of the negative of imaginary function of just function divided by the real just function, and the result is given as for proton oxygen scattering phase shift. We can see that for low energy binding energy, E lab starting from 0.4 to 2 MeV, that we have calculated the phase shift as given as is almost agrees with the experimental data. You can see. So our calculations establish that the nucleus potential model have ability to fit all the low experimental data. So here we can see that from the figure 1 for E lab energy is equal to 0.60 MeV. The graph between the scattering cross section and the phase shift, that our data, our calculated data is almost agrees with the experimental data. And in the second graph for E lab energy 0.80 MeV, that is almost satisfied with the experimental data. And the third this angular distribution curve for the proton oxygen system, the graph between the differential cross section and the phase shift there is some deviation, but that is almost agrees with the experimental data. And here we calculated for S wave only, and we can calculate it similarly further for the P wave or L equal to 0, 1, 2, 3 and so on. Thank you.
Yeah, any questions, please? Yeah, Arishi, go ahead.
Can you hear me?
Yes, ma'am.
You have taken the value of screening radius A equals to 55 per centimeter.
Yes, ma'am.
Is any criteria to set the value of A?
Ma'am, you have to set the parameter of a long range because we have to take the electromagnetic in short range.
But the nucleus radius is up to 15 femtometer. So 55 is much more than this. It's in third slide.
Explain 2017. C41. C41.
Does A equals to 55 femtometer?
Yes, ma'am. If we fit actually we are trying to fit in the computer programming. So it almost satisfied with the experimental data, and so we are taking the A equal to 55 centimeter.
And alpha and B for the Manning-Rosen?
We are taking just because it is satisfied with the short range.
Okay.
Thank you very much. Ishtiaq, now you can. Oh, sorry. Rangajalu sir, please.
I just have a quick question. The reference 4 you mentioned there as the data points, is that the cross-section data or experimental data?
Which page?
Reference 4. You are mentioning the reference 4.
Show reference 4, no?
Yeah, reference 4. The data points you are showing, the Dubrovsky, these guys, Dubrovsky code. This is experimental data, experimental cross sections.
I didn't get it.
Are they experimental cross sections? This reference 4 that you are quoting as experimental, are they really experimental cross sections or derived ones?
Yeah, that's the question.
Sir, she's only MSc student, she doesn't know much.
Yeah, no, I got it. No, but I just was curious because that's, yeah, okay, thank you.
Thank you, sir.
Ishtiaq.
Yes, sir. Okay. So can you see my screen?
Yes. Make it crispy or you are all taking too long. You're taking as much as...
Yes, I will
try to keep your talk to within 8 to 10 minutes and then 1 or 2 questions so that, but there are many more students you have to give.
Yes. Okay, so good afternoon everybody. This is Ishtiaq Ahmed from IUAC. I am working here under the supervision of Dr. R. Kumar. And the title of my talk, as you see, is Electromagnetic Structure of Zinc Isotopes using Coulomb excitation. Now I will be talking about, I will just give a brief introduction of Coulomb excitation, the technique of Coulomb excitation, and then the experiment which we recently performed for the zinc isotopes basically. And then some of the results will be presented. So starting directly from the Coulomb excitation. So as many of you must already be knowing that when two nuclei approach each other, so because of the charge of projectile as well as the target and therefore the electromagnetic field which is acting, the time-dependent electromagnetic field, the nucleus gets excited. So now either the projectile will get excited or the target will get excited, or both of them can also get excited. So that is basically the transfer of energy to the nuclear excitation energy. So that is what is known as Coulomb excitation, as I am trying to show it here in this illustration. And when you see the right hand side, when the excitation takes place, the nucleus goes from a ground state to, for example, let us suppose to the first excited state. And later on, after depending upon the lifetime of the state, this will decay and it will emit either a gamma ray or a conversion electron, as you already know. So from this gamma ray is basically the characteristic of that nucleus. So the beauty of Coulomb excitation is that this is not the thing that the nucleus gets excited, but the real beauty is that this excitation cross section is a direct measure of the E lambda matrix elements. And from the E lambda matrix elements, then we can calculate various nuclear properties. For example, the reduced transition strength, and from the diagonal matrix element, you can calculate the quadruple moment, and from the quadruple moment, you can calculate the shape, etc. So here I show the usual Rutherford cross section, as you know, from the elastic scattering. This is very well known, and for the Coulomb excitation differential cross section, this will be multiplied. The Rutherford cross section will be multiplied by another term Pn, which is nothing but the excitation probability. So this is it, and then this Coleman citation is basically, as I told you, that this is the most direct and powerful tool of studying nuclear shapes and collectivity. So why is this direct? Because the cross section is a direct measure of the lambda matrix elements. And here I am trying to show you another illustration in the left hand side. For example, this is the transitional matrix element, this K2, 2 plus to 0 plus. So from here you can calculate the V2 for the 2 to 0 transition. And also when you go when you see in the right hand side of the screen, you see that there is a transition also between these M states. Here in the right hand side I show it from 0, 1, 2 and 0, minus 1, minus 2. There are the M states, and the transition occurring between these states is basically the reorientation effect. And from this reorientation effect, basically you calculate the quadruple moment, the intrinsic quadruple moment, for example. So from the reduced transition strength, therefore you can calculate, you can not calculate, but you can show the collectivity of a nucleus, and also from the quadruple moment you can show the shape, you can measure the shape of a nucleus, for example. And the other advantage of Coulomb excitation is that this is a pure electromagnetic interaction. As I told that this happens because of the time-dependent electromagnetic field between two nuclei. So this is being an electromagnetic process, this is a model-independent method to probe the nuclei. Unlike various other techniques which are in the field, for example, the Doppler shift attenuation method, the RDM method, and various other methods which are used in this field to measure the nuclear properties. This Coulomb excitation has the advantage of being model independent and also the electromagnetic interaction. Okay, a few other basics of the Coulomb excitation. For example, in order to explain the excitation properly, we have to have the classical way of
इसमें हम आए ना देख लेना है लॉगिन वगैरह है ना
नहीं कोई आज का एक्सेप्ट कर देना आप देख लो ऑनलाइन देखना
but the picture fails very soon when you consider other properties, for example, the reduced transition strength, the quadruple movement, etc. That is what has also happened in the cadmium isotopes. So, if you can look, if you have some time, you can go to this physical review letter of Paul Garrett, where he has shown that in cadmium isotopes, a similar kind of behavior was there earlier, and then later on, they have shown that this is no more a vibrational nucleus. Similar kind of story is also here in the zinc isotopes. So if you see, for example, 64 and 66 zinc and K equal to 0 and K equal to 2 band, then they were suggested as quasi-rotation from the enhanced interband transition and also from the weak intraband transition. In interband is from 6.1 to 4.1 to 2.1. Intraband is from 6.1 to maybe 4.2. Okay, so sorry. And also, if you look at the 66 zinc, they are also from the reduced strength for the E2 and for the M1, a gamma sort of interpretation was given for the zinc 66 zinc. Now, again, you look at the zinc isotopes, you see the energy of EX2 to, I have plotted the EX to E first excited state on the y-axis, and then on the x-axis you have the zinc isotopes. So this is the ratio of 2 phonon triplets to the first excited state. Okay, for all the zinc isotopes. So from the standard geometrical model that is, for example, the Billet-Jeans model, you will see that most of the nuclei 64 to 62 to 70 zinc, or maybe 76, 78 zinc, they are lying in this limit. That is the limit of vibrational and the non-axial gamma soft proton limit. But if you see the ratio of the 0 to plus state again, now remember that 0 to plus we were discussing earlier also. So this is going a little odd again here. So this is different again. So we needed to examine it a little more carefully. Now you also look at the reduced transition strength for the zinc isotopes. So these are the measurements from different laboratories over the world for the reduced transition strength from first 4 plus state to the first 2 plus state for the zinc isotopes. So from the Munich, from the Isolde facility, from the Ganil, and from the LNL Italy facility. Particularly for the 70 zinc, what you see here is that there is a huge difference between the two values of the different laboratories, and also there is a big error also in this LNL 2013 measurement. So that was also a very good case to study that what exactly is the reduced transition strength for this nuclei. And then going further, in the case of quadruple movements, if you see for zinc isotopes, again you see that in 66 and 68 zinc, some experiments are suggesting that the quadruple is negative, the others are suggesting that the quadruple is positive. So this is not, I mean, you cannot understand this thing that why somewhere it is negative, other, I mean, this is not possible. How can a nucleus can have a negative quadruple and at the same time it has a positive quadruple moment? So because then this will have different shape. So that was also a point of motivation for us. So we went ahead and we have performed the experiments for 3 isotopes, as I mentioned, 64, 68 and 70 zinc. So I am directly now coming to the analysis part. So we have made the Doppler correction. Now for Doppler correction you need the precise geometry of the experimental setup. So that is what I am telling here, that you need the geometry of the setup. Because geometry, I mean the angle, the precise angle where the Clover angle, the Clover detector and the other PPAC detector is basically positioning, and from there you can Doppler shift correct the spectrum, the gamma spectrum, and from this expression, using this expression, where this E gamma 0 is the unshifted the original energy, and E gamma is the shifted energy, and this V2 is the velocity, and theta gamma 2 is the angle between the gamma detector and the particle detector. This is again the setup geometry, so I will just skip it, I think. And now directly coming to the polar angles of the PPAC, so we can calculate the information of the, I mean the theta angle of the PPAC using this expression, and from the delay lines as well. So I think you must have attended the talk of Dr. R. Kumar yesterday. So there he was explaining in detail about this particle detector. So from those delay lines you can calculate the theta of the particles, and also the phi of the particle. Phi of the particle will be calculated from here. So you have a cake-like structure of the PPAC, and when you calculate the average of, I mean overall this will be 360. So when you divide it, then you can get an angular pitch, and from there you can calculate the phi angle. So you have the theta, you have the phi of PPAC, and now for the Clover detectors. So initially we just perform a very basic measurement to just estimate the theta and phi of the Clover, but later on we do a theoretical calculation, and from there we can precisely calculate the position of the crystal, gamma crystal, where the gamma ray is actually going. So from this plot that can be done, and therefore we calculated the theta and phi for the Clover crystals. So after you calculate the position of germanium as well as the position of the PPAC, then you can precisely correct the spectrum, gamma spectrum. Okay, so calibration efficiency, as you know that this is a very basic thing. You have to perform the calibration and the efficiency. That is what I have shown it here. I will just quickly skip this because of the lack of time. So now these are the Doppler corrected spectrum. So this is the spectrum for 64 zinc. I have split it into 3 parts. the first half and the middle part and the right half. So here what we see is the different transitions which are coming from 64 zinc and after Doppler correction, and also for the 68 zinc we have, and then for the 70 zinc. So from this information then we can develop a level scheme, a level structure for a given nucleus. So right now I have only shown it for 68 zinc, for example, here. Now what you see here is that this is a close collision case and this is a partial level scheme. Energies are in kV, of course. So the previous measurement which was performed was by Koizumi in 2004. So these red lines are from that paper, and the blue lines are the one which we got in our experiment, and the black ones are, of course, that they are common. They were found in that Koizumi measurements also, and also here at IUS. So after that, once we get these transitions, we will calculate the intensity. From intensity, then we can get the matrix elements. The matrix elements, remember, which I showed you much earlier in the first slide. And from the matrix elements, then we can calculate. Then we can get the information on reduced transition strength. And if from a diagonal matrix element, then you can get the information on quadruple moments and then on the shape. So this way we are planning the next analysis from this experiment. That was all. So now the summary, as you see that, as I mentioned, that Coulomb acceleration is a very powerful tool to study the nuclear collectivity and nuclear shapes in particular. And these isotopes, that is the zinc isotopes, are a good testing ground for various theoretical models because of the large variation of nuclear structure around in its vicinity. And the Coulomb experiment, the Coulomb acceleration experiment was recently performed for the zinc isotopes at IUAC, and Doppler corrected spectrums for these three nuclei I have already shown you. Thank you very much.
Any questions? Sir?
Yeah, I have a question for you. You mentioned, if I heard you correctly, that 5 femtometers is the separation distance you consider to be corresponding to safe energy. Am I correct?
Yes.
Is it from edge to edge, or is it from the center to center of the two nuclei?
Oh, no, not from center to center, from edge to edge.
So what is the total distance between the center to center?
From center to center, it will be around maybe something like 15 femtometer, depending upon the radius of that nucleus, particular nucleus.
So then you got to calculate what should be the energy of. So what is your energy calculation based upon? That's what I want to know. Because if you think about a spherical sphere, which is when you make the safe energy calculation,
Yes.
Are you putting in the radii of the two nuclei of the colliding nuclei into consideration or not?
Yes, of course. We are putting the radius of the collider and target as well.
I missed that.
Yes.
That helps me quite a bit, in fact. Okay, now once you do that, and then if you do that, you're assuming to be purely Coulomb excitation. But then when you see all the other rotation structures and 4+, 2+, everybody coming into the picture, how do you reconcile that you may not have nuclear interactions in addition to the electromagnetic process of, when you say it's a Coulomb excitation, how sure are you that is a Coulomb excitation only and no nuclear complications? That's my question.
Yes. So that is basically already included in this +5 Fermi. So this +5 Fermi is not just random.
No, I'm not talking about that.
Really, you forget. After getting the output, how can you make out it is only purely excitation, Coulomb excitation?
Exactly, that's my question.
No, yes, I understood your question that how sure we are that this is a pure electromagnetic interaction, right?
Yep.
So that we are only looking at the safe energy.
Young man, I tell you, this has been done for 50 years. And I did the electron scattering myself. Working with it, assuming a pure electromagnetic interaction, I can extract the nuclear structure to the finest extent. That I really burnt my days and nights doing that. Okay? It is only an approximation. It is not a total correct theory. I can explain to you, I can give you lectures on that.
Yes, Rakesh sir.
Yeah, the answer actually what is actually one of the answers, but I would like to. Can you hear me? I think you can hear me, right?
Yes.
The thing is that the safe Klein's energy is a very definite formula to calculate safe energy, where you have no more Coulomb interaction at all. and in principle we are much below than that, and we are in very much safe place that there is no nuclear interaction happening. That clearly shows by the decay of only gammas. If we have some nuclear interaction, then some sort of fusion reaction also will take place. And some other things will also come out.
Some sort of what reaction?
Some sort of fusion may be there if you are approaching above the barrier, or you are having the nuclear part in it, you know.
No, but there can be many other things, right? Other than fusion, there can be inelastic collisions.
Yes, of course.
Yeah. See, you can't say it is only electromagnetic. There can be inelastic collisions. There can be pickup reactions.
But
it's not only fusion.
They have been designed as such that it will be only electromagnetic interaction. And the energies which you are getting are much below than that. For example, what I explained in my talk in tin, the safe energy is 220 MeV, but we have performed an experiment at 175 MeV. So, just to give an example about it,
Right.
So what I was saying that this pi Fermi is not random. This has been seen from many previous experiments that when you use this kind of formula, you get a safe energy, and then from that safe energy, you are sure that the nuclear interaction is less than 0.01%. So this is from the literature only.
Literature is okay, but see, as a scientist, our job is to question everything. Okay, right.
That is true. That is true. Okay. Shastri ji thi hai, badhiya hai. Okay.
Okay, Sushil. Now actually, Ishtiaq, I told you to stick to 8 to 10 minutes, but you have taken almost 20 minutes. Okay.
Yeah, but
good talk.
Is not well, and he may not give his talk.
Yeah, it's a nice talk. Okay, let us go to Sushil now.
No, sir, I have taken the time of Sushil also. So he is not here.
Oh, you covered both.
Well, actually. He's not well, actually.
Okay.
Just keep his talk, please.
Right. Okay. Then let's move to Navjot Kaur, please. No, the talk was good, Ishtiaq, but questions are must.
Yes. Thank you.
And questioning is the purpose of this things also. I will apologize.
Navjot Kaur, are you there? I thought I saw her.
No, sir, you had put a very good question, actually, you know. And this is what is the question which is asked by many physicists to us about this nuclear part, actually. It's a very valid question, actually. I appreciate you that you have looked into this. Since nobody cares about it and you have just cared about it.
Rakesh ji.
That's a very, very good question.
Rakesh ji, actually, I will have a discussion with you later on because, it will take very long otherwise.
Okay, please carry on.
It's important even in our simulations also. When we are working in our simulations, we need to understand why that pi Fermi is important. Yeah.
Sure.
Right, thank you. Navjot Kaur, madam. Hello. I think, okay, she seems to be there, but she's, yes.
Hello, yes, good afternoon, sir.
Good afternoon, yeah. Could you please start your presentation, please?
Okay, sir.
Kindly share your screen.
Yes, sir. Wait a minute. I'm going to share. Please let me know when it is visible. Is it visible, sir?
Yes, you can make it full screen, please.
Okay, shall I start?
Yes. Madam, you are research scholar or assistant professor?
No, sir. I am a research scholar.
Okay.
A very warm good afternoon to all. So, myself Navjot Kaur. So, today I would like to talk to you about decay of copper isotopes and related nuclear structure effect using the collective clusterization approach. So, these are the contents of my today's presentation. So, firstly, I will talk to you about the introduction, Then I'm using the basically DCM model, that is dynamical cluster decay model. So I will discuss about the formalism which I'm using. So next calculations and discussion, and finally I will talk about the summary and conclusions. So this is the basic introduction. So in the nuclear reaction, we have studying reactions are different scale of energy, like high energy nuclear physics, intermediate energy nuclear physics, and the low energy nuclear physics. So basically, I am working on the low energy nuclear physics. That is the beam of less than 50 nm per nucleon. So in 1936, our one of the Danish physicists, Niels Bohr, he give us the compound nuclear reaction theory. So in this, firstly projectile incident on a target nucleus, and then we have a formation of the compound nucleus, and further it has some decay products. So it is shown here on the schematic diagram. So next I'm going to talk about the DCM formalism, that is based on the QMFT, that is a quantum mechanical fragmentation theory, uses a collective clusterization approach. So preformation probability of a preformed cluster is calculated by the solving a stationary Stringer equation in mass fragmentation coordinate is given by this equation, and it having some mass asymmetry parameter or a charge asymmetry parameter. Next, we have a fragmentation potential. Fragmentation potential is comprises sum of binding energy plus 3 potential, that is Coulomb potential, angular momentum potential, and the nuclear proximity potential. So binding energy comprises of two terms, that is the macroscopic liquid drop model plus microscopic shell correction part. And in this we have a two potential, that is like Coulomb potential and angular momentum potential, or we can say that centrifugal potential. Basically these are repulsive potential, and nuclear proximity potential is an attractive potential. Another type of probability we using, that is the penetration probability, is calculated using the WGKB approximation. The expression for the penetration probability is given over here, where RA and RB are the turning points. One of the RA is the basically like we can say a starting point of the tunneling, and RB where it's the terminates. So VR is the total interaction potential as a function of separation distance, and Q effective is the effective Q value of a decay process. So next is the calculations part. Basically, I am working on some isotopes of the copper, that is 59, 60, and 61 copper. So the excitation energy of the compound nuclei formed in different mass regions using the given reaction channel with the specific center of mass energy resulting in the temperature. So here firstly we have a ECM for these isotopes. Next we have a excitation energy, temperature, Lmax. And similarly we have a delta R, that is the impact parameter, and we have a cross section that we have calculated using the dynamical cluster decay model, and next we have experimental cross sections which we have carried out from the experimental paper. So calculations and discussion. So firstly I will talk about the fragmentation potential for the 59, 60, and 61 copper. So figure 2 and figure 3 and figure 4 for these fragmentation potential for these isotopes. So figure 2, figure 3, 4 represent the variation of total fragmentation potential with the fragment mass number A2 for deformed compound nuclei 59 copper, 60, and 61. As it is quite evident from the figure 2, 3 at L is equals to 0, the PS drastically changed with the LPS competing with the SF symmetric fragments, and SF's 30 is highly dominant for the case of 59 copper, and similarly for the So if we're talking about when we move from 59 to 60 and 61, in the graph we look for that. In the case of 59, we have a 30 phosphorus is dominating, but on the 60 copper, we have a 29 silicon, and similarly for the 61, we have a 31 phosphorus. But when we look for the preformation probability for these isotopes, in this trend, the dominating parts get the giving the high peak. Suppose in this we have a 6 lithium that is in the dominating area, but for the preformation probability, it is showing the inverse trend. It has it giving us the maximum. 6 lithium is on the maximum part, but on this it's showing the least behavior. So 5, 6, 7 represent the preformation probability as a function of fragment mass for the decay of 59, 60, 61 copper. Actually, the preformation probability follow the inverse trend of fragmentation profile as analyzed through the variation of the relative preformation probability with the fragment at L values. So next we have a scattering potential for the nuclei 59, 60, 61 copper. Figure 8, 9, 10 represent the scattering potential for the decay of 59, 60, 61 copper at different L values. The scattering potential for the compound system 59, 60, 61 copper is plotted for the mass number. As we can say that at the L minimum we have a more barrier height, more space, but when we go for the maximum angular momentum, then it gets decreased for all the sections. So next we have a variation of summed up preformation probability for the nuclei 59 and 60, 61 copper. Figure 11, 12, 30 represent the variation of summed up preformation factor with angular momentum for 59, 60, 61 copper decays via light particles, intermediate mass fragments and symmetry mass fragments. So the summed up preformation decreases with increase in the value of L for the light particles, but it increases for the intermediate mass fragments. So light particles are those particles whose masses lies between 1 to 4, and intermediate mass fragments are those whose mass is between from 5 to 20, and similarly symmetric mass fragments are those whose mass lies between 21 to 30. So this trend we can show from these graphs. So the summed up preformation show always similar trend to the light particles on the compound system under study. Calculations variation of summed up penetration probability for nuclei 59, 60, 61 coppers. So in this figure 14, 15 and 16 represent the variation of summed up penetration profile with angular momentum for 59, 60, 61 copper decay via light particles, intermediate mass fragment and symmetry mass fragments. These figures show that the summed up preformation is negligible for the light particle and intermediate up to the maximum L value approximately. After L equals to 30, it start increasing with increasing in the value of the L. Variation of summed up cross section for nuclei 59, 60, 61 copper. So figure 17, 18, 19 represent the variation of summed up cross section with the angular momentum L 59, 60, 61 copper decay via light particle and intermediate and symmetry mass fragment. We noticed that the trend of variation due to the combined effect of the summed up preformation and the penetration probability. So it is the combination of these two quantities. So the fragmentation profile of compound nuclei 59, 60, 61 copper formed in 35 chlorine plus 24, 25, 26 magnesium reaction is studied here as the collective clusterization process for emission of both the light particles as well as the intermediate mass fragments within the GCM. We explored that the structure of the fragmentation profile is mainly due to the binding energy, which is subsequently affected by the interplay between attractive nuclear proximity potential and the repulsive Coulomb potential. Moreover, the inclusion of temperature also affect that all the three contribution of binding energy, proximity potential and Coulomb potential. The additional effects of angular momentum potential at a higher temperature further affect the total fragmentation potential. The competition among the light particles, intermediate mass fragments and symmetry mass fragments, asymmetry fragments in 59 copper, 60 and 61 copper been analyzed with their preformation profiles. The scattering potential for the compound system for these nuclei, we have analyzed that the barrier modification decreases at the higher L values, reflecting increases in the penetrability. The L summed up penetration probability of all the preformed fragments as a function of L values, we see that the comparatively for compound nucleus 59 copper, the penetrability is significantly high. Moreover, the values of cross-section are plotted for the light particles, intermediate mass fragments, and symmetric mass fragments. We notice that the trend of variation is due to the combined effect of preformation and the penetrability, and cross-section value gets modified accordingly to the product of these quantities. Thank you.
Please.
Okay, Navjot, how you have fixed the maximum value of angular momentum?
Okay, sir, actually, we have segregate the mass regions like light particles, intermediate mass fragments, and symmetric mass fragment. So what we do, firstly, we calculate the cross section only for light particles, like collectively from 1 to 4, and we got a one graph. Like whenever we at a point where we get the constant value over the rest of the fragments, so we assume that that is our Lmax value, maximum angular momentum.
So this is not the property of your incoming channel.
Yes, sir.
This is not the property of your incoming channel. This means you are getting it from your outgoing channels. That is your variation of light particle cross section with angular momentum.
Yes, sir. Actually, where we get the constant value, because there are the number of the decay fragments. So we got at one point, rest of the fragments gets the constant value. So at that point, we got the constant values. So we assume that this is the our Lmax.
Okay, thank you. We next move on to Danny Rose.
Yes. Can I present screen?
Yes, please make your presentation.
Okay, and the screen is visible, right?
Not yet.
Okay.
Try to choose entire screen. Go to present mode and choose entire screen. Yeah. Your screen is not visible right now.
Visible right now.
Yeah, now it's visible. Now make it full screen.
Okay, sure. Okay,
Yes, right. Now you can start.
Okay. So my presentation is on nuclear structure studies using HSB-CHO, and this was carried out at Department of Physics, Cochin University of Science and Technology under the guidance of Dr. Ryan Kumar A.K. And as part of my work, I investigate the ground state properties, potential energy curves, and the temperature dependence of some of the properties for the isotopes platinum, osmium, mercury, and polonium in the framework of Kine-Hartree-Fock-Bogleubov theory. And in my investigation, some of the ground state properties which are investigated include binding energy per nucleon, 2 neutron separation energy, the charge radii, RMS radii, and the quadrupole deformation of these nuclei. Again, the work the work was done, or the computations were done using the CORD HSB-CHO version 2.0, which essentially gives the axially deformed solution for Kine-Hartree-Fock-Bogleubov equation in the transformed harmonic oscillator wave. Discussing the theoretical framework of Hartree-Fock-Bogleubov theory, this is essentially a self-consistent mean field framework which generalizes the Hartree-Fock theory and the BCS theory. The Hartree-Fock theory describes the nuclear field, while the Bardeen-Cooper-Schreiber theory helps to explain nuclear pairing correlations and incorporates it into the Hartree-Fock theory. Coming to the Hamiltonian, in second quantization, it can be written in the form in terms of particle and creation annihilation operators as given in equation 1, where the first term is the kinetic energy and the second term gives the interaction, which is the anti-symmetrized two-body interaction matrix element. Again, to incorporate the pairing correlations, we transform the particle basis to a quasi-particle basis, and that is the creation and annihilation operators to a quasi-particle creation and annihilation operators through a Boglie-Born transformation as shown in equation 2. This transformation can equivalently be written in the form of the matrix as in equation 3. Again, defining the one body density matrix rho mn and the pairing density matrix kappa mn, we perform the variation of the energy or the variation of the Hamiltonian to obtain the eigenvalue equation HFD equation. So HFD equation as given in equation 5 is an eigenvalue equation, and we diagonalize this equation to obtain total energy and other properties of the nuclei. Coming to the form of HFD energy used here, the HFD energy is written in terms of the local energy density functional HFR, which is a function of the nuclear density and its derivatives. The terms included are the kinetic energy, the Skyme interaction, which gives the interaction potential between two nucleons, the pairing energy, the Coulomb energy, and the corrections due to spurious motion of the nucleus. Again, the Skyme force has a form given in equation 9, which is essentially an expansion in terms of momentum and density, and the spin current of the nuclei. The pairing and Coulomb interactions are also as given in the equation. So substituting these values of energy and solving the equation using the course, we could obtain values for different properties of the nuclei. And so I will move on to discuss some of the results I have obtained. The first property that I calculated was the binding energy per nucleon for these isotopes, 16. As we move from a lower neutron number to a higher neutron number, we have obtained values for binding energy of these nuclei, and also at different temperatures, 0 MeV, 2 MeV and 4 MeV. As expected, once the temperature is increased, these nuclei tend to expand and thus have a lower binding energy than those in the ground state 0 MeV. Again, these calculations were done for two Skyme parameterizations, SLY4 and UNE0. We can see that in the ground state these agree pretty well, but then as we move to higher temperatures, there is a discrepancy seen between the calculations done using two parameterizations. Also, the experimental values in the recently published experimental data seems to agree pretty well with our computed values wherever available. Also, the two neutron separation energy, which is the energy required to remove two neutrons from the nuclei, were also calculated for these isotopic chains. These two again agree well with the experimental values. Also, at the magic nuclei of n equal to 126, we see an extra stability, which is shown as a dip in the graph. And the interesting result is that as we increase the temperature, this extra stability of the magic nuclei vanishes. That is, there is no such noticeable difference in the two neutron separation energy at magic nuclei n equal to 126. This is because the shell effects tend to vanish as the temperature is increased. and n equal to 126, we do not see an extra stability there. Again, the proton and neutron radii for these isotopes were also calculated. Even when the proton radii, even when the proton number for an isotope is proton radii increases along with the neutron radii, this helps to compensate for the Coulomb interaction or the repulsion between the new neutrons that are introduced. They counteract to the repulsion between the two new neutrons introduced. So the neutron skin thickness is essentially the difference between the proton and the neutron radii. As the number of neutrons increases further, an outer crust which is devoid of protons is formed, and this outer crust, which has only neutrons, is called the neutron skin thickness, and it can be used to correlate astrophysical properties of say even the neutron star. And so studying the neutron skin thickness is of importance. And here we have studied the temperature dependence of the neutron skin thickness for these isotopes. As the temperature is increased, we see a clear increase in the neutron skin thickness of the nuclei. Again, the charge radii was similarly calculated, which gives an idea of the charge distribution in the nucleus, and these calculations also had pretty good agreement with the experimental values. Again, both the calculations using two parameterization gave pretty good agreement. Also, the quadrupole deformation that gives or that explains the shape in the nuclei were also studied. The nuclei usually has a spherical shape at the magic nuclei n equal to 126. Again, the nucleons, as we increase the neutron number, they tend to oscillate between prolate and oblate shape. They tend to oscillate between prolate and oblate shape. Also, interestingly, as the temperature is increased, the neutrons tend to be more spherical, and the numerical value of the quadrupole deformation, be it prolate or oblate, it decreases and moves to 0. That is, as the temperature increases, the nuclei tends to be more spherical. Also, the potential energy curves in these isotopes were investigated to study shape coexistence. And while studying some of the isotopes of these nuclei, we could find many of them having shape coexistence. Shape coexistence is essential. So, while considering the potential energy curve, the minimum of the potential energy curve usually corresponds to the ground state shape of the nuclei, and when there are two minima or almost two simultaneous minima, we say that these nuclei has shape coexistence and can exist in both of these shapes. So while investigating these isotopic chains, we could find many nuclei that had, some of them had two prolate shapes coexisting, some of them had two oblate shapes coexisting, and some had even prolate and oblate shapes coexisting. Also, this confirmed that there is shape coexistence in these nuclei. The results for the platinum, osmium, mercury and polonium are shown here. Also, the calculations for both the parameterizations are pretty similar, and so these are my calculations, and we possibly aim to look into the possibility of examining the discrepancy between the calculated and experimental values in both the parameterization when we move to higher temperatures. And also, further we plan to study the equation of state of nuclear matter and its relation to the equation of state of the neutron star, and thereby link our theoretical predictions to experimental observations, as there are many experimental observations going on in these nuclei, especially like the discovery of bubble nuclei and other shape.
Yeah, any questions? Dalit,
yes, sir. Danny Rose, can you show me your slide number 8?
Okay. Yeah.
Here you are showing that proton and neutron radii calculated for even isotopic chain.
Yes.
And this proton and neutron radii are chaining with neutron number. What it means? How the radius of a proton or neutron can be something like 5.2 Fermi or goes up to 6.3 or 6.4 Fermi. I think there is something wrong in this. This may be the radius of some nucleus or charge radius, or it may be matter radius, but it cannot be proton or neutron radius. Am I right?
But like, why can't it be the proton or neutron radii? I didn't get
Look at the caption of your
Yes.
figure.
Yes.
So you are writing here proton and neutron radii.
Yes.
So proton and neutron radii cannot be of this order, and will increase with neutron number. I doubt there is something wrong.
the heading should be, I think, the radius of plutonium and osmonium with adding proton and neutron.
Yeah, it may be like that. It means that
No.
she must be calculating the density distribution, and from
Yeah.
there she may have taken
Yeah.
the central
Yeah,
radius.
This is the calculated from the density distribution of
Yeah, so
the protons and the neutrons.
but this is not for proton and neutron. This is the radii for these isotopes, charge radii or mass radius, you can say.
Increasing number of neutrons.
Okay, so you mean like not the single proton and single neutron you are talking about?
Yeah. Because
Okay,
the language-
sorry.
That's what you have written there.
Okay.
That's why it's
Okay, I
confusing.
didn't get that. Okay, sure.
Fine.
This is actually the RMS radii calculated from the density distribution of proton and neutron.
And neutrons, yeah.
Okay.
So these are the central
See the
radii.
terminology. Yeah.
These are central radii.
Yeah.
Charge radiation, matter radiation.
Yeah,
I got a quick question. Maybe just wondering, you mentioned in your talk that as the temperature increases, the system tends to be more spherical.
Yes.
And I thought generally the common sense intuition, generally what we see in nature is as the temperature increases, the system tends to be more deformed and expand rather than being contracted. And
Yeah.
to my mind, so that's not somehow counterintuitive to think the system becomes more spherical, more ordered as you increase the temperature. Can you respond to that?
In a general sense, obviously it expands, and this expansion is more or less uniform as we increase the temperature. It is not that it gains more order. It definitely loses its order and maybe deforms or expands, but still, as a whole, the chances are that maybe the deformations are equal in all directions to make it. I'm not sure of.
Hard to believe though, but maybe I'm wrong.
I think she may be talking about the vanishing of cell effects at that particular time.
Yeah, vanishing is a cell effect. Yeah.
Thank you, Danny Rose.
Thank you very much.
Now I request Nabil Salim to take charge. Yeah. Sorry, did somebody else raise a question?
Hello?
Yeah, Nabil, please.
Is it audible?
You can stop presenting. Yeah. Did anybody else raise a hand? I didn't know. Sorry. Okay, let us continue because we have very less time. Already we are running short. It's already getting close to 4 o'clock. Nabil, please show your screen and start the presentation. Kindly stick to 8 to 10 minutes. Yeah, you're all going very to introduction. Yes, Nabil.
Is it visible now?
Yes, you can start.
Good afternoon. My name is Ramesh Lane and I am from Cochin University of Science and Technology under the guidance of Dr. Ryan Kumar K. So I am here to present on the topic the effects of thermal pairing on nuclear properties. So this is the outline of the talk. So first of all, as an introduction, I am going to talk brief about what is nuclear pairing. So you have all learned about the basic nuclear models. So from the liquid drum model, you have learned the semi-empirical mass formula, and you know that there is an extra term called the pairing term in the semi-empirical, the Weizsäcker formula. So how does that term came to be? So that term came as a result of the existence of nuclear pairing. So I am going to give a short evidence of the nuclear pairing. So one of the evidence is the odd-even staggering, which means that the even nuclei has an extra stability or has extra binding energy compared to the adjacent mass number nuclei. So how does then an even nuclei has an extra binding energy? So they can be easily visualized when we plot the separation energy. As an example, we can plot 1 neutron separation energy of any isotope chain, and we can clearly see that. So I have here plotted the 1 neutron separation energy of the 10 isotopes from 50 to 89, and here you can see 3 plots. The one is in the red is the experimental data that we have taken from the paper that I given the blue. Then there is a liquid drum model in the blue line, and the liquid drum model without the pairing term as in black line. So you can see that the zigzag nature that is shown in the experimental data cannot be explained without the pairing term in the liquid drum model. So when adding that term, we can match the experimental data. So that's why an extra term, a pairing term, is added to the liquid drum model. And the large dip in the n equal to 82 and 50 is due to the shell effect, and that's why we have the shell model. So this is the basic introduction of nuclear pairing. So pairing interaction is that it is an attractive interaction between two neutrons with the same quantum number except the projection of their spins. And the pairing also affects the even nuclei as its ground state becomes a 0+ state for all even nuclei, and there is an energy gap that we call it the pairing gap in the even nuclei far below the collective states. Then the nuclear pairings due to the short range part of the nuclear-nuclear interaction, and there are other evidences like the existence of 2+ states, as in the previous presentation of the Zn isotopes. You have seen that there is the all even nucleus has a ground state of 0+ states, and there is a 2+ state in the as the excited states. So these are all due to the nuclear pairing. So to properly study what the nuclear pairing, the Bohr, Moritz and Pines, who was the pioneer to introduce the theory to explain nuclear pairing, that came from the VCS theory, the Bernstein-Cooper-Schrieffer theory that explained the superconductivity in metals. So these the pairing in superconductivity and in nuclei are somewhat similar or analogous to each other. So we look at the theoretical framework, which is the finite temperature VCS model that we have used to study here. So the Hamiltonian of the system with a constant pairing interaction strength G can be written as H is equal to Hp minus lambda n minus gamma m, where Hp is the pairing Hamiltonian, lambda is the chemical potential, n is the particle number operator, and the gamma is angular velocity, m is the position of total angular momentum operator. So here we have studied here we are going to study the effect of pairing both in temperature and in finite angular momentum. And the pairing Hamiltonian is shown here with the single particle term and the interaction term in the second conversation form. Next, with the Hamiltonian, we after diagonalizing it and after Bogolubov transformation, we get the grand potential omega as shown here. So by minimizing
You can go a little more faster, Salim. All this we have seen.
Okay.
Yeah, because you see, you are given only 8 to 10 minutes, but you are taking almost half an hour. Like that, it's going to look.
Okay, sir.
Yeah, move to the results.
Okay. So by minimizing the grand potential, we can get these three equations. So by solving these three equations numerically, we can study the effect of pairing in temperature and in angular momentum. So move on to the results. So here you can see the temperature effect of pairing in the neodymium isotope 146. So as temperature increases the pairing gap decreases and it vanishes, and the effect of angular momentum is that as angular momentum increases, the pairing gap also decreases.
Slide is the old slide. You haven't moved to the new slide. These are the results.
These are the results, sir.
I don't see that here, so I see the old same theoretical framework.
No, the slide is moving. Yeah, the slide is changing. No.
Maybe a problem on my end. I don't know.
Its problem is at your end, sir.
Okay. Can you see the slide pairing gap?
Yeah.
Yes. Continue. We are able to see. Yeah, I think, sir, you have to refresh your screen.
Okay, sir. Okay. So here we get a critical temperature in neutron pairing to be 0.352 MeV with a critical angular momentum of 5h², and in the case of proton it is 0.671 MeV critical temperature and a 14h critical angular momentum. So next, the effect of pairing in excitation energy and entropy. As you can see in the plot, as temperature increases, the effect of pairing can be seen visually in the excitation energy plot and the entropy plot. As pairing vanishes, there is a phase transition happening in these thermodynamical quantities. And in the next slide, we have the heat capacity and level density. Similarly, as before, the heat capacity also shows a phase transition. The proton and neutron pairing vanishes. In the case of level density, we have compared the level density with the actual experimental value observed reported in the Oslo data, and we can see that the theoretical and experimental values correlate each other. Now, as a conclusion, we have studied the finite temperature BCS model in the case of neodymium 146, and we obtained a neutron and proton pairing gap of 0.615 MeV and 1.186 MeV, and the thermodynamic quantities like entropy, excitation, and the heat capacity and the density are plotted, and the phase transition is visible in these quantities. So, and the level density matches exactly with the data at excitation energy E greater than 1 MeV. Thank you.
Yes, sir. Continue, please.
Nabil, how you have calculated this critical temperature?
Okay, this critical temperature, as in the finite temperature BCS, as we solve by giving each temperature, like we input each temperature and find the pairing gap. So as we increase the temperature, we can see that the pairing gap reduces and it vanishes.
So what is the range of that energy or temperature at which it vanishes?
It vanishes. So I have given here the neutron pairing gap vanishes at 0.352 MeV, and the proton pairing gap vanishes at 0.671 MeV. As the plot is given in, it is a normalized plot, that is the T by TC plot. That's why the plot vanishes at 1 MeV.
So you are saying this is around 0.352 MeV of energy.
In the case of neutron, and for the case of proton, it is around 0.671 MeV.
Okay, fine. Thank you.
Okay, thank you, Nabil. Any other questions? Right. So I request now Jyotish.
Thank you, sir.
Hello, sir. Am I audible? Yes, you're audible. Please show your screen.
नर्सरी में नहीं यूकेजी में एलकेजी साढ़े 3 का होता है ना एलकेजी में यूकेजी में
Is it visible now, sir?
और
Make it full screen. So.
अच्छा तब पापा ने ड्रॉप करना है सर तो कर लेना पापा ने कर लेनी उनसे बात है
Yeah. Okay. I can start. Okay. So good afternoon, everyone. My name is Jyotish. I am doing PhD under the guidance of Ram Kumar from Cochin University of Science and Technology. First of all, I would like to thank organizers for considering my paper for the International Conference on Recent Trends in Nuclear Physics. Thank you for this valuable opportunity. Today, the topic of presentation is a study on nuclear observables using
न्यूरल नेटवर्क पर बंदे आ गए
बस तब देखना हमने उसको बंद करो.
So, if we have a bunch available data, then we can efficiently use artificial neural network method for analyzing the data. So, in nuclear physics, because of the rich availability of the experimental nuclear observable like binding energy, beta decay energy, alpha decay, etc., nuclear physics is an excellent candidate for ANN method. So, this is the brief outline of my presentation. So, let us go through the definition of artificial neural network. So, artificial neural network is a computational model based on structure and function of biological neural networks. So that means ANN works like how the biological neural network works. So here we can see the figure. This is shows how artificial neural network and biological neural network connects. So basically I am not a biology student, so I am just going through some basics of human nervous system. Here it consists of...
go to the main methodology, Jyotish.
Okay.
Yeah, don't worry about introducing artificial neural networks.
Yeah, okay.
Discuss
okay.
how artificial neural networks are using to study nuclear structure.
Yeah. So we have different types of artificial neural network like DNN, deep neural network, Bayesian neural network, convolution, and recurrence neural network. So here, in this presentation, we are using deep neural network method for finding total binding energy and beta decay energy of the system. So the deep neural network consists of input layers, output layers, and hidden layers that shown in here. So each layer consists of a number of neurons. So these neurons connected with the activation energy. So activation function. This activation function is one of the main thing in how the neural network going to work. So this is act as a transformation function. So it transfers the information from one neuron to other. That means it is the deciding factor that whether the signal or information can transfer or not from one neuron to other. So here we have used rectified linear unit as an activation function. We have different types of activation function like tangent, sigmoid, etc. So here ReLU function equal to maximum of 0, s. This is the equation of our activation function. So for finding the loss function, we have used for the error function, we are used mean absolute. The equation is 1 by n sum over I equal to 1 to n yi cap minus y. So where yi is represent the value predicted by DNN and yi represent the true value. So by using this, we are finding binding energy and beta decay energy. So for this, for the for developing the DNN model, we have used 3,560 experimental nuclear data sets for the training and validating our DNN model. It is taken from Ripple 3 and IAEA data. So from our DNN model, our primary inputs are neutron number and proton number, and secondary inputs that can be derived from the primary inputs, that is promiscuity, parity, magic number, asymmetric term. These all terms can be derived from the primary input. The equation is shown here.
So this is the schematic diagram of our DNN model. It consists of two primary input and 8 secondary input and 115 3 hidden layers, with each 3 hidden layers consist of 512 neurons, and our two outputs, binding energy and beta decay energy. So out of 3560 experimental value, 70% of the randomly taken data are used for the training, and the rest of 30% is used for the validation of our model. So result and discussion. So for getting better result, so we have iterate our model up to 500 times. So in order to get our error become minimum, that means minimum loss, and our output will be more accurate with the experimental result. So here our minimum loss becomes 0.105 MeV for the training set and 0.188 MeV for the validation set. So this is the comparison between predicted nuclear observable value with experimental result. So here this is first diagram shows the binding energy, and second diagram shows the beta decay energy. Here from the first diagram, so mean absolute error is we got 0.131 MeV, and from the second diagram, the binding energy, the mean absolute error for the binding beta decay energy got 0.88 MeV. So interestingly, so when we are calculating the binding energy using finite range drop model, so we got mean squared error is up to 0.59 MeV, and if we are using a Hartree-Fock-Bugly-Bow method, then we got mean square error is 0.518 MeV. So we can just compare our mean square error and our already theoretical the already existing theory. So we can see this artificial DNN model is far better than the FRDM and HFT. So this is the graph, the prediction of binding energy per nucleon and beta decay energy of the nucleon in the entire landscape. So from the figure itself, we can see the binding energy is almost located at the 8 MeV. So that can be derived the experimentally also we can verify that. So this is the total binding energy and beta decay energy of the entire nuclear landscape. So this is I plotted the binding energy per nucleon and beta decay energy of some selected particular nucleus like calcium, bromine and cesium by varying the neutron numbers and compared it with the experimental result. So here we can see here I plotted this blue line represent the experimental result, this green line represent the our predicted model result, and just adding the liquid drop model result also. So here from the figure itself we can see our model and the experimental model are very much correlated. So similarly in binding energy case also, so these both two experimentally and predicted value are correlated with each other. So our conclusion, the machine learning technique of DNN is used to predict the total ground state binding energy and beta decay energy of the atomic nuclei. So 3560 nuclear data are used for the training process, and it is found that the predictive power of the DNN model is depending on total number, total input number, hidden layers, neurons inside them, and activation function. So the predicted value of binding energy and beta decay energy using DNN model are very much comparable with the experimental results, and interestingly our FRDM and HFP models, the far better model we got. So thank you for your kind attention.
Let me see.
Yeah, please go ahead, Ayush.
Am I audible, sir?
Yes.
So I want to know that what is activation function?
So activation function is a function which is connected between each neurons. So it's a mathematical function after all. So basically in older days for the regression method, people are using y equal to mx plus c equation. So from this equation, this m is that m can be said that function, but now people rely on if data become more complex, then we can use a rectified ReLU function or like sigmoid function, tangent function, etc.
Okay. Actually, in the FRDM and all, they use root mean squared error, right? As the cost function.
Yes, sir.
But you have chosen mean absolute error.
Yeah. Actually, in my model, I can only choose the mean absolute error. So I just try to find here mean squared error also I found. So this is, we got 0.103 MeV for binding energy. So what I did means I just take the square of root mean square error of that FRDM and HFP. So I got 0.59 MeV and 0.518 MeV.
From their values.
Yeah.
Something is not all right. It's okay. Check it out again, because anyway, of course, you got the thing right.
Yeah, this is almost prediction is getting right.
Because root mean squared error is of the order of 0.39 in case of generalized liquid drop model, which is generalized liquid drop. I don't know the exact values of FRDM, so I can't say anything. But from FRDM only generalized liquid drop model has been derived. So
yeah.
Maybe you should compare with generalized liquid model, because FRDM is a very old model.
It is old model.
Yeah, you should take a generalized liquid drop model and then check with the comparison. Okay. And even then you should compare root mean squared error, not mean squared error, because they are not given that. Yeah.
Yes. Okay.
But what will you do with this result?
So result means we can like
two things I didn't understand. See, when you are using deep hidden networks, deep neural networks, you don't need to give actually any other input, but you have given a secondary input as well.
Yes. So actually first we tried for only this primary inputs. So we didn't get that much accuracy. So that's why we go for the secondary input like.
So then it becomes some. That means basically you're giving some information from physics, right?
Yeah. Yes.
Yeah. So you can't simply call it deep neural networks, because deep neural network is something which will learn these things on its own.
Yeah,
so
actually
when you're providing some inputs which are related from already known. See, if you wouldn't have given this asymmetry and magic number and all these things, then if it can by itself, if it can find out the relationships, then it's a deep neural network. Yeah, that is the main difference between deep neural network and ordinary neural networks.
And
or artificial neural networks, what we call as. Okay.
Yes.
So that is where the machine learning stops at where in machine learning you still have to give these inputs, but when you go to deep neural networks, you don't need to give any other input regarding the various things. Anyway, because you called it deep neural network, I wanted to make it clear to you. Okay.
Yeah, right. Programming actually we have.
It's good, very nice. You have done good work. Okay.
Yeah.
From where you have to begin, right? After you begin, then you start working, then you'll get better results. Good.
Yeah. Yes, sir. So,
right. Well done.
Yeah. Thank you.
Okay. So I think we have one last and final participant, Gokul A.
Yes. फिर से कुछ नहीं. न्यूरॉन तरह कौन एक्ट करता है यहाँ पे न्यूरल नेटवर्क में? इसमें रिलेशन होते हैं मैथमेटिकल इक्वेशंस.
Yes, Gokul, please present your screen to us.
Especially nucleus.
Slightly increase your volume.
Especially nucleus.
Just a minute, sir.
क्योंकि तो हर जगह यूज हो सकती है. हर कहीं. हर चैप्टर में जहाँ रहता है. मैंने क्या एक इक्वेशन से सब कुछ फाइंड आउट करना. एक इक्वेशन बाकी डाटा इनपुट दो और वो दे देना. एक से ज़्यादा इनपुट होगा तो डीप लर्निंग में.
Sir, is this visible?
Yes, you are visible and audible. Continue.
Good afternoon, sir. I'm talking about clustering effects and neutron vision. AI. I'm from the Department of Physics, Continuing Science and Technology here. Now, this will be the overview of my topic, the formalism. And then I'll go into my results in the and then I'll conclude my topic. From stars to galaxies,
the tendency to form clusters is seen throughout the universe. Actually, the occurrence of molecular states. I mean, this idea of clustering was predicted in the early 1930s. As time went, after the discovery of oil shale and all, in 1960s, the radical methods dedicated to this particular phenomenon. And in 1968, the theories on the molecular light structures came out. It was Ikeda in 1968 who popularized this idea of the clustering. He studied the alpha clustering effects in the foreign nuclei. His paper, entitled "The Systematic Structure Changes into the Molecular Light Structures, the Self-Conjugate Foreign Nuclei," this was discussed. He said the nucleus, atomic nucleus, moves into an alpha conjugate structure at specific excitation energies, and he simplified these results in a diagram called the Ikeda diagram. In the diagram, as we see, suppose we take a neon nucleus which has a mass number of 20. At a certain excitation energy, it moves into a clustered state of a foreign alpha conjugate nuclei like oxygen and then alpha nucleus, which will be 16%. Pieces. 11.89 as the energy increases, the nucleus change into a state of 2 alpha and a carbon nucleus, and so on. So this is the Ikeda diagram, and he popularized this idea. Now, moving into my theoretical formalism, I will be discussing relativistic Hartley Bouguereau theory. This is a microscopic theory, and microscopic theories has been successful in explaining the nuclear structure. Theories like relativist mean field models and Bouguereau approach have been widely used to study many body problems, and it has also applied to nuclear cluster studies. The underlying benefit of using these theories is that it considers both the scalar and vector fields in the nucleus. Now, going to the theoretical formalism, upon applying the mediation principle, we get the RST methods as shown, where HT is the Dirac Hamiltonian, and S of this form, where S is the scalar, is the attractive scalar potential, and V is the repulsive vector potential, and we have the mean pairing gap delta with the pairing field. Now,
Hello? Some problem? Gokul?
It seems to be there's a problem, so they're not here either. And then now he's back again. But I can't see anything on the screen except the talks for the last couple of months.
Okay.
But that's my problem. That's my problem, not from your problem. But then now it just left. You're back, I can hear.
Actually, I thought I was having problems, so I just refreshed my screen. But then I think he has got problem. Gokul must be coming back.
Sir, I lost my internet connection in the lab.
No issues. No issues.
Yes, yeah. It is reconnecting now.
Yeah, please. Yeah, please show your screen.
As an example for my before going into my work, I'll be showing the localization of conjugate, the alpha conjugate nuclei. So, with my studies, I have studied how the structure of nuclei is related to the cluster effects, how it changes with the deformation parameter. For a beryllium-8 nuclei, the deformation of zero spherical nucleus, as shown here in the figure. As we increase the deformation, we can see it attains a state of at 1.19. It moves into a clustered state with like a 2 alpha nuclei, and considering a carbon 12, which is of 3 alphas, and here also at 0.0 we have found it to be a spherical. But at minus 0.29 beta 2, we have an equilateral triangle-like structure. It is actually seen as tumbled as a triangle, but the other studies have found that this is an equilateral triangle with the third cluster in the middle of the part, so visible with the difference in localization from the pods. As we increase the beta at 2.33 range, we attain a 3 alpha linear chain like structure.
वो होता है